when you're presented with a definite integral, you have a choice to make. I'm going to show you the choice that I would make, and I'll explain the other way, but I really don't like the notation. And this does say there are two ways to substitute. If you watched my other practice video on indefinite integrals, hopefully you'll understand there are two ways to substitute for u, and that's u could be secant of x, and du could also be tangent of x, because in either case, we can deal with, we can deal with the du. Everything's left over. That's actually not what I mean. When, in this case, I'm talking about these bounds of integration. Okay? And it's not really that there are two ways to substitute, there are two times to substitute. Because, I don't know, the way my eyes are drawn to this problem, I see that I like u as tangent of x, but there's nothing wrong with the other version, which would make du equal to secant squared x dx. As we write in everything, well, tangent of x becomes u, secant squared x dx becomes du, but we can't write 0 and we can't write pi thirds, because each of those are x values, not u values. So we can't put those things in here. So this is the version I don't like. The version I don't like is, okay, so we'll have an indefinite integral out of a definite integral. I suppose then we can say, well, I guess that has an antiderivative 1/2 u squared plus our constant. We really don't need a constant since technically we have a definite integral thing going here. And then I guess, what should I say? From x equals 0 to x equals pi thirds, that's going to be 1/2 tangent of x squared plus c evaluated from x equals 0 to x equals pi thirds. From there, I'm sure you can figure out substitute pi thirds, substitute 0, and subtract. I don't like that way. What I like instead is not changing a definite integral to an indefinite integral and then back again. And so what we have to do is use u equals tangent of x. So when u is equal to tangent of x, that means tangent of, let's use the x value, pi thirds, that u, tangent of pi thirds, is the square root of 3. That means we can also do tangent of 0 is 0. Wrong color, want to make these match. And so now this is sort of nice. We already took care of the tangent part. We even changed the 0 and the pi thirds using that rule about tangent. And so, bonus time, or I don't know what you want to call that, we don't have to change back to tangent of x when we're done because 0 and root 3 are already used. What's the antiderivative of u with respect to u? 1/2 u squared, and we're going to evaluate from u equals 0 to u equals the square root of 3. 1/2 the square root of 3 squared minus 1/2 the square root of 0 squared is 3/2. So the difference, I suppose, is because we did this work changing the upper and lower bounds of integration into u values of 0 and square root of 3, we didn't need to resubstitute after we found an antiderivative. You don't need to do that twice. I believe I showed you on the last page. So hopefully you can see 1 minus 2x cubed has a derivative involving x squared. And, oh man, I have to show the substitution. So I'll say u is equal to 1 plus 2x cubed, which would make du 0 plus 6x squared dx. And I don't have a 6x squared dx, so I'll make a 6x squared dx by multiplying and dividing by 6. So 1/6, 6x squared and dx become du. The square root of u. All right, what happened to our bounds? So when x equals 1, u equals, do you have it? 3. And when x equals 2, u equals 17. How did we do that? Well, let's think about this. So u is equal to 1 plus 2 times the x value cubed. If that x value is 1, the lower bound of integration, maybe we should do this in different colors. If that x value is 1, u is going to be 1 plus 2 times 1 cubed, or just 3. And u is 1 plus 2 times the x value cubed. If that x value is 2, 2 cubed is 8, times another 2 is 16, plus 1 is 17. So here we go on 17. Well, the square root of u is u to the 1/2, so the antiderivative of u to the 1/2 is u to the 3/2 times 2/3, and we're going to evaluate from u equals 3 to u equals 17. Now a minor point here, but I think it's a major point. A lot of teachers and textbooks would just write a 3 here and a 17 here. Why not do that? Well, because we substituted. And so I guess a common error would, instead of having 3 and 17, you might screw up and have a 1 and a 2. So I'm hoping that by saying x equals 1 and x equals 2, the original x equals 1 and x equals 2, you might realize, oh no, I can't put x's where u's are. Oh right, I was supposed to change these to u's or change the u's back to x's. So if you're writing, well, this is u equals 3 because I did the thing, hey, u equals 3, and this is u equals 17, I did u equals 17, I'm allowed to put 17 for u. That's what I'm hoping. But your mileage may vary. So 1/6 times 2/3 is 1/9, and we are going to do the square root of 17 cubed minus 1/9 times the square root of 3 cubed. We can, of course, simplify the square root of 3 cubed, but I don't think that's what we're worried about today. I'm going to stop there and let you practice on your own.